In the early 1700s, when muscle power did most of civilization's work, a new sound rang out over the English countryside, a sound that was to mark the beginning of a revolution. It was not the sound of gunfire like most revolutions, it was the sound of power, power that would change the course of human civilization. A young engineer named James Watt had invented the steam engine. Monstrous in size, low on power, and not very reliable, this smoking, noisy contraption introduced the Industrial Revolution, the era of machine power. Finally, portable power, a machine that ran on its own, one which could carry out the heavy chores of plowing the earth, grinding wheat, operating sawmills, running factories, and eventually carry people and goods across vast distances. Today we've refined that power, and we use it to carry our heavy loads across the land, to carry them across the oceans. And it's power that we've used that's enabled us to learn how to fly. This is immense power that we can control at the touch of a finger. So why is machine power so important to measure? Because muscle power cannot do work as quickly as machines. Machines were invented because they can do more work in less time. But what is power? Power is related to work. We saw in the work unit that work is done whenever force moves something a distance, or when torque rotates an object through an angular distance. In fluid systems, work is done when pressure moves a volume of fluid. And electrical work is done when voltage moves an electric charge. But remember how we learned that it doesn't matter how long it takes to do work? That as long as the force, the distance, and the weights are the same, the amount of work is the same? In a technical sense, the person on the stairs and the high jumper are doing the same amount of work. So what's the difference? The high jumper is doing the work in a much shorter time, consuming energy at a faster rate. That's power. Power is the rate of doing work. If work is done in a shorter time, it takes more power. Since the time it takes to do work usually is important, that is, we want to get the work done as quickly as possible, power is important to measure. Machines that are powerful usually do work in less time. So although the tractor pulling this jet is doing the same amount of work as the jet would itself rolling under its own engines, the tractor takes longer to do the work. Therefore, it uses less power. The tractor could pull the plane all the way across the country, but it would take months. People on the plane would rather use more power and get there in less time. But let's look more closely at this formula. There's something interesting within it. We've seen that work in, for example, a mechanical system is force times the distance the object moved. If we put it over time, that's power. Distance over time is speed, and speed is a rate. So another way of looking at power is to say that it's force times a rate. Either way, you get the same answer. This means that for the same amount of power, you can use a lot of force and move slowly, or less force and move faster. These are the considerations that are made in any field when matching power to the job.
Agricultural tractors are manufactured from approximately 12 horsepower to 500 horsepower. The critical thing is matching the tractor to the job to the tractor. The larger the farm, generally the larger the tractor, because there's more acres, more ground to be covered. There is a point that we reach of diminishing returns where two smaller, lighter tractors possibly would be more efficient than one large tractor due to the weight.
For some applications, two smaller tractors pulling small implements can do the job faster than one large tractor pulling a large implement. A big tractor has more horsepower, but the smaller tractors are faster. A big tractor pulling a large load works at a slower rate. These are the considerations a farmer has to make when trying to match horsepower to the individual job. In a rotational system, power still depends on force times rate. Here, torque is the force and rate is the angular speed. For power in a fluid system, pressure acts like force and the rate is the volume flow. In some cases, we have a changing pressure. But we can also have a changing volume. But it's still generally a force times a rate. In the electrical system, power is the product of voltage acting like force and the current. In other words, a volt times an ampere. Thermal power is even easier to deal with. Thermal power is the rate of moving heat energy from a warm place to a cold one through a temperature difference. But that movement is exactly the same as a thermal rate. In other words, thermal power and thermal rate are the same thing. We already saw thermal rate in the rate unit. We've come a long way since the donkey. The amount of work we do today is not that different from 200 years ago. We just do work much faster today. When we're talking about doing work as quickly as possible, we're talking about power, and that's a powerful message. We've completely surrounded ourselves in power. It comes in many different forms, and we use it for a lot of different purposes. The amount of power that we have on hand and the type of power that we use will determine how quickly we get that work done, or the rate at which we do that work. It's an important consideration when it comes to efficiency. We're also using up energy. And I think, didn't we already do potential energy? Doesn't it become kinetic energy? It takes force to do work, and whenever work is done, it takes time. When we want to do work in as short a time as possible, we need to calculate power, the rate of doing work. But increasing power has its trade-offs. More power means more energy. So sometimes it may be worth taking a little more time to do the work and use less power. Any machine that does mechanical work needs to be rated according to the amount of power it can deliver. That ability then has to be matched with the amount of power needed to do the job in a given time. When James Watt invented his steam engine in the 1700s, he had to somehow measure the amount of work it could do. So he measured the newtons of force it could deliver, or the foot-pounds of torque it could apply to a shaft. But since the main advantage of his new machine was that it could do work faster than an animal, time had to be an important factor in his calculations. Work does not involve time, so it had to be a new idea. That idea is power, work divided by time. The unit of work he chose was the Newton meter, the unit of time, the second. And since James Watt came up with the idea, that unit of power is named after him, the watt. The problem with the watt, or the Newton meter per second, is that people at the time did not use those units to measure power. They were only concerned with how many animals it took to do the job. Well, since Watt wanted to sell his machine to these people, he came up with a unit that compared his machine to a donkey. A donkey was the main source of power in England during the 1700s. It can exert a force on another object. which is why they're useful doing work, when they cooperate. Watt figured that the average donkey could pull with a force of about 550 pounds and move an object 1 foot in 1 second. Now he had all the ingredients to measure power. Force applied through a distance is work. And since the work was done in a certain period of time, in this case 1 second, Watt now had a unit of power, the rate of doing work. For Watt, that unit was 550 foot-pounds of work done in 1 second. Either Watt loved horses or he hated the sound of the name donkey power because he called his new unit the horsepower. Too bad for the donkey. Horsepower was a unit that people could relate to, and one which we still use today. Horsepower ratings can be given for situations where straight pulling is useful. The faster we want to go, the more power it takes. Measuring power is also handy where straight pushing is applied. But in most cases, horsepower needs to be calculated right where it's delivered, usually through a rotating shaft. The calculation for power in a rotating system is the same, the time it takes to do work. Work in a rotating system is torque times angular distance. The time is still in seconds. The result will still be the same units, foot-pounds per second, which is usually converted into horsepower. But let's back up just a little. This formula for power, torque times angular distance over time, can be expressed in a different and perhaps easier way. Angular distance over time is a rate, like revolutions per minute or speed. So power can also be found as force times rate in the rotating system. That's torque times omega. Whatever method you use to calculate horsepower, the result is the same. You can either measure the amount of work being done and the time it takes to do it, or you can measure the force produced by the machine and its speed. Both methods are a measure of power. When power out is compared to the power in, you have an excellent way to measure the efficiency of the machine. Usually, power is delivered through a system of gears and linkages. However, some power is lost because of resistance of the moving parts. The result, say in a tractor, is that the amount of power that reaches the wheels is less than the amount of power put out by the engine. For Herb Cargill, understanding the power requirements of agricultural equipment is part of his job.
For a tractor to operate efficiently, we do two different things with it. One is a drawbar horsepower, which is the effort that the tractor can exert in pulling a load, such as a disc, a plow, a blade, a car out of the ditch, whatever. The other horsepower is a power takeoff horsepower that is utilized through a mechanical shaft to a gearbox, another hydraulic pump, a generator, an alternator. We can use this mechanical horsepower in different ways. Agriculturally, it's used to run choppers, rotary tillers, different types of farm implements. But two things happen. The power takeoff horsepower is generally greater than the drawbar horsepower. The reason being that the drawbar horsepower is transmitted over to the wheels, through the axles, and to the ground. Slippage occurs on the rear wheels in pulling a load. Consequently, the effective horsepower is a little less. For example, a power takeoff of this particular tractor, horsepower-wise, will be approximately 40 horsepower. The drawbar horsepower will be about 37.5 to 38 horsepower. There are several different methods that power can be transmitted or that we can use the power takeoff horsepower. Other applications would include mounting a hydraulic pump on the power takeoff. The power takeoff, the tractor horsepower, would then turn this hydraulic pump. That hydraulic pump could be used to run hydraulic cylinders, hydraulic motors, many fluid power applications. Many farms also have standby power. They take the tractor, hook it to a generator. If the power goes out, a power shortage for some reason, the farmer can still continue to milk his cows, pump his water, do his operation at the farm. Just the mechanical transmitting of power to a gearbox is only one of the applications that power takeoffs can be used for.
Technicians working with power conversion like transmissions, torque converters, and power takeoff must know the power at all points throughout the system. Too much power could damage the machinery. Too little, and the job is not done properly. Likewise, they need to know the efficiency, the power out compared to the power in. Here's an interesting project. Think about how many devices you use every day that develop power. We use power to push, pull, lift, and lower objects of different sizes and weights. We also do that work at different speeds. If you add up all the power you've used since you got up this morning, that's a lot of donkey power. Fluid power. Moving fluids from one place to another with pipes and pumps, or using fluids to move a mechanical device, like the actuators on these robots, or hydraulic cylinders on heavy equipment. Power in a fluid system is similar to power in a mechanical system, the rate of doing work. Only instead of how fast or how slow we do the work of moving an object, fluid power is how slow or how fast we do the work of moving a fluid. We've seen that sometimes fluid work is done when pressure moves a volume of liquid or gas. We've seen that fluid work is done when there's a pressure difference, or delta P. To turn that work into power, we simply put it over time. The pump in this tanker truck has to do the work of lifting fuel up to the tanks in the wings of the aircraft. The pump is overcoming a pressure difference between the tank on the truck and the tanks in the wings. The rate of doing that work is the power of the pump. The same is true for the pump that fills this water tower. It takes more than an hour to do the work of raising the water up and filling the tank. During the launch of the space shuttle, the entire contents of that tank are emptied in a matter of minutes to provide cooling for the launch pad. Gravity does the same amount of work as the pump, but it does it much faster, so there's more fluid power on the way down than there was on the way up. We've we've also seen the second way of doing fluid work, when a constant pressure displaces a volume of fluid, such as a piston pump. To turn that work into power, we divide it by time, or measure how quickly or slowly the piston does the work of displacing the fluid in the system. Delta V. These two ways of measuring fluid power are units of work over units of time. Like mechanical power, we can see a rate hidden within the general formula for fluid power. The general formula for power is work over time. In a fluid system, work is pressure difference times volume. Pressure acts like force in the fluid system and causes the fluid to move. But volume over time is a fluid rate. So we can also measure fluid power as pressure times flow rate, or generally, force times rate. Either way, you get the same answers. It was fluid power in the form of steam that enabled James Watt to operate his engine. Although most steam engines are gone today, steam power is still behind some of our most powerful equipment, like these steam turbines at a generating station. Very often, fluid power is used to control mechanical power. Ed Larson assembles very large engines. The power of the engine starts with the fluids that enter the cylinders. In engineering lingo, a cylinder is a jug.
This is a 16-cylinder marine engine. It runs about 115 horsepower a jug, about 1,600 horsepower. We're going to talk just a little bit about how fluid power, we turn fluid power into mechanical power and into the rotational power of the crankshaft. These gauges tell the conditions of the different fluid power components we have on this engine. One is fuel pressure, jacket water temperature, jacket cooling water. We have engine oil pressure that lubricates the engine. Right here, under this valve cover, is where the power for this engine starts. We have a fuel coming in these manifolds to a unit injector. As the piston comes up, this is how we get our power. The injector sprays atomized diesel fuel into the cylinder, and it ignites under the temperature of compression, driving the piston down in the power stroke, down in the cylinder of this engine. This is the piston for this engine over here. The amount of power this engine produces is related to three things. The volume, or the size of the piston we have in the cylinder. The rate, or the RPM. This engine you just seen runs about 1,800 RPM. We can run it as little as 1,000 RPM. Or we can change the pressure. These engines are designed to run about maximum pressure, so we can't increase the pressure to effectively increase horsepower. So what we do is go to a larger engine with a larger piston, and this gives us more volume in the cylinder and gives us more power. This piston to this piston runs about 115 horsepower a jug. The engine that this piston goes in runs about 300 horsepower a jug. The reason is we have more volume and more fuel-air mixture driving the piston down. But we can do it this way without increasing effective compression ratios. After this gas drives the piston down into the cylinder, we collect the exhaust gas through the exhaust manifold, and this exhaust gas drives a compressor turbine, and it draws fresh air and actually runs in a boost condition to feed these cylinders so they don't have to draw air in through a vacuum, and makes it more efficient. After we take this power out of each of these systems and turn it into rotational power on the crankshaft, we come out, we'll bolt this engine to a generator or marine transmission, and from then to a propeller on a boat. On many of these engines you'll see, if you see tugboats on many of the larger rivers, the Mississippi or the Ohio, will have engines in them like this, and either 2 or 3 at a time.
Fluid Fluid power is very popular because it transfers power with very few losses. These brushes operate with fluid motors. Hydraulic oil moves through the motors, causing them to spin. The pressure to move the oil through the brushes comes from one pump. So little power is lost in the fluid, the pump can very efficiently transfer its power to all the brushes in the car wash. If the same thing was done with electric motors on each brush, it would be a much more costly and less efficient method. Fluid power. It determines how fast we move a fluid. Sometimes lives depend on how we control it. It's measured as the rate of doing fluid work. And sometimes controlling fluid power can help us control power in other systems. So we can try silly things like this. Electric power was introduced as the clean, modern route to the future. Now it's entered so many aspects of our lives, modern civilization could barely get along without it. Think of what your day would be like without electric power. Electric power must be precisely controlled, not just because of its own value, but because we usually use electric power to control other forms of power. Like mechanical and fluid power, electrical power is the rate of doing work. Or work divided by time. But instead of the work of moving objects or fluids, electric power is the rate of moving electric charge. Electric work is done by voltage moving coulombs of charge. To turn that into power, we simply put that work over time. But does this look familiar? Q over T, or quantity of charge moved in a period of time, is a rate. We saw in our rate unit that a coulomb of charge moving through a wire in 1 second is 1 ampere. Isn't it convenient that an ampere is a rate? That means that we can more conveniently use our second formula for calculating power. Force times rate. Voltage is the force, amperes or current is the rate. In other words, a volt times an amp is electric power. Electric power is expressed in watts, named in honor of our friend James Watt. The wattage rating on a device tells us the amount of electric power it consumes. The meter on the side of a house shows the power consumption of the building. The wheel in the center of the meter runs at different speeds depending on the amount of power being used by things like appliances and electric heaters. The faster that wheel spins, the more power is being consumed. In other words, the faster the wheel spins, the faster the money goes out the door. The gauges measure the watts of power by the thousand, or kilowatts. The power companies are not just interested in kilowatts of power being used by all the appliances in the house, but also how long that power is used. So the meter is also measuring time, or the number of kilowatt hours. You'll be dealing with this meter in more detail in your laboratories. Power companies must constantly change their power outputs as the demand changes. Every day there are 2 electric rush hours, one in the morning and one in the evening when people turn on all their electric appliances to cook meals, usually at the same time. The power into a device is only half the story. If we also measure the power out, we measure efficiency. This is an important consideration because some devices, like a laser, are not very good.
Well, what you see in front of me here is an argon laser, and it's a gas laser, and it's water-cooled. Now, lasers of this type require a lot of power, a lot of electricity, and they're very inefficient. What that means is this laser will require about 20,000 watts of electricity for about 1 watt of laser light out. So that means about 20,000 watts of power has to be dissipated by the water cooling. So what happens is the electricity comes across the tube at the 2 ends and heats it up, and the water cooling is wrapped around in coils that go from the back of the laser towards the front. So by wrapping in coils like this, it does pretty much sufficiently cool the laser.
Usually electric power is turned into some other form of power. In this case, it's light and thermal power. Very often, it's turned into rotational mechanical power of turning a shaft. If we want to measure the efficiency of a motor like this, we have to compare the mechanical power out to the electrical power in. Fortunately, Mr. Watt made that easy for us. Remember that James Watt calculated a mechanical watt as a joule per second. But the joule is also a unit in the electrical system, so we can easily convert from mechanical watts to electrical watts. In fact, they even have the same value. We can even go further than that and compare electrical watts to horsepower. It turns out that 1 horsepower is equal to about 746 watts of electrical power. By comparing electric power to other forms of power, we're able to match electrically operated devices to specific jobs. Electric motors are good for heavy loads because they're self-starting. There's no need for clutches and transmissions. They're also capable of tremendous speeds. The fastest trains in the world are electric. The main limitation is how much power can be delivered to the vehicle. By the way, if you'd like to see a precise control of voltage and current, both the opening title of this program and these effects were done by the laser you just saw. Heat. From the moment we wake up in the morning, we're using it in some form. We either use heat for its own sake, to heat our bodies and cook our food, or we try to control how it moves from one place to another, or we turn it into some other form of power, like mechanical power. But if we try to fit thermal power into the general concept of power, that is, work divided by time, we find that there's no such thing as thermal work. Heat is energy. Once heat is generated, it moves from a warm area to a cold one on its own. Temperature difference is what moves heat, so one way of moving it faster is to increase the temperature difference. But what you're really doing is increasing the rate at which you produce heat energy. In other words, thermal rate and thermal power are defined the same way, and they use the same units, BTUs per hour or calories per second. The difference between thermal rate and thermal power is one of application. Thermal rate is used when we're concerned with the movement of heat energy, such as radiators, which try to move it as quickly as possible, and insulators, where we're trying to slow down the rate of heat flow as much as possible. Those are thermal rate applications. Thermal power is used in three situations. The first is where heat energy is produced for its own sake, at certain rates, such as in hair dryers and furnaces. The second is when thermal power is converted into other forms of power, such as electricity, which is produced from the thermal power in the furnace of this generating station. The third is when we unintentionally generate thermal power, and it lowers the efficiency of another system because of heat loss. This friend-foe relationship with thermal power is important to consider because it's so common in technology. But whether we call it thermal rate or thermal power, it doesn't matter. The calculations and the units are the same. All machines generate heat, whether it's intentional or not. What is important is to make sure that the right amount of heat energy moves to the right place in the time it's supposed to. We have completely surrounded ourselves in power. Power to move the earth and move ourselves. Power is the rate of doing work, or how fast or slow we get work done. These two cars are the same weight, move the same quarter-mile distance, so they're doing the same amount of work. But one of them does work faster than the other. It's a little more powerful. And it wins the race. The same amount of work done in a shorter time using more power. Power is a useful concept because it works across all four energy systems. In a mechanical system, it's the rate of doing work moving objects. In fluid systems, it's the rate of doing work moving fluids. In electrical systems, the rate of doing work moving electric charge. And in thermal systems, the rate of heat energy flow, or thermal rate. It's very convenient that a rate is built into this formula, so we can also measure power as a force times a rate. This makes it even easier to see how power works across all four systems. For the linear mechanical system, power is force times speed. The rotating mechanical system has torque acting as force, and the speed is an angular speed, or RPM. In the fluid systems, pressure difference and volume flow rate determine power. And in electrical systems, power is voltage times current. Can you see what all these definitions of power have in common? Force, torque, pressure difference, and voltage are all force-like quantities. They all act like force. While speed, angular speed, volume flow rate, and current are all rates. So you can say that generally, if you can find the force in a system and the rate at which it's moving, you can find the power, no matter what system you're working in. Technicians working with powerful machinery must know how to match the power to the job, to be able to use the power most efficiently. That means it's also necessary to decide how fast the work needs to be done, because that will affect the amount of power needed. This transporter, for example, is the largest land vehicle in the world. It's also the slowest, with a cruising speed of 1 mile per hour. It has so much work to do, just carrying its heavy load, that increasing its speed would mean an enormous increase in power. In this case, the slow movement is not a problem. But in other cases, speed is important, so the more power, the better. This program was produced at the facilities of Telemation Productions and is part of Principles of Technology, a project of state and provincial vocational and technical education agencies in association with the Agency for Instructional Technology and the Center for Occupational Research and Development. Together, serving education.